Now, let us understand the second type of mechanical energy, that is potential energy. Basically, the potential energy is the energy stored in any object. It is energy stored by virtue of the configuration of the object. There are two types of potential energy. One is gravitational potential energy and the other is elastic potential energy. The gravitational potential energy is the energy stored in object by virtue of its position. For example, an object is kept on surface of earth and then it is lifted up by height h. So here, due to the position of this object, it has gained some potential energy, that is called gravitational potential energy. The elastic potential energy, the energy stored by virtue of shape, is called elastic potential energy. The best example of elastic potential energy is the energy stored in spring. The energy is stored due to deformation, that is change in shape. This is called elastic potential energy. Now let us understand both the energies one by one. First, gravitational potential energy. The gravitational potential energy is the work done in raising the body to height h from surface of earth. If this is surface of earth, this is body of mass m. We want to raise it by height h. So we have to apply an upward direction force that is equal to at least its weight. So F is equals to mg and the displacement is h. Work done is F as cos theta. So work done will be equal to mgh and that is called the potential energy of the object. The relation between force and potential energy is given by f of x is equals to minus del u by del x. Here f is the function of x. If we integrate on both the side, we will get integration f of x dx is equals to integration of minus du and that is equal to ui minus uf. So integration f of x dx will be equal to change in potential energy. Now let us see one example on the relation of potential energy and force. Given the potential energy as a function of x, y and z, that is potential energy is distributed in all three dimensions as x square y plus xyz plus y square z. We want to find the force acting at a point 1, 1, 1. The relation between force and potential energy is F is equals to minus del u by del r. So the vector F will be equal to minus of del u by del x I cap minus del u by del y j cap minus del u by del z k cap. Here del means the partial differentiation, so we have to do the partial differentiation of this term. We will do it one by one. First differentiate it with respect to x. So we will get x component of force. So fx is equals to minus del u by del x, that is equals to minus del by del x of the value of u is x square y plus xyz plus y square z. Now while we differentiate partially with respect to x, the other terms y and z are considered to be constant. So fx will be equal to minus of differentiation of x square y will be 2xy, differentiation of xyz will be yz, and differentiation of y squared z, as y and z both are constant, it will be 0. Now let us find the fy, that is minus del by del y of x square y plus xyz plus y square z. So it will be minus of the differentiation of x square y with respect to y is x square plus xz plus 2yz. Same way, finding the z component, minus del by del z of x square y plus xyz plus y square z, that is equal to, the differentiation of this term will be 0 plus xy plus y square. We want to find the force at 1, 1, 1. So fx will be equal to x square y, so 1 plus 1, this is fx, that will be 2 plus 1 plus 0, that will be equal to minus 3. The fy, 1 plus 1 plus 2, that is minus of 1 plus 1 plus 2, that is minus 4, and fz, that is equal to minus of 1 plus 1, that is equal to minus 2. So the force is given by minus 3 cap, minus 4 j cap, and minus 2 k cap. So this is our final answer. Now let us see conservation of mechanical energy. The total mechanical energy of the system is conserved if the forces acting on it are conservative. The meaning of conservative force is that work done by the force in closed loop is 0. Then it is said to be conservative force. For example, the gravitational force. If the work done is not 0 in the closed loop, then it is the non-conservative force. So now let us prove the conservation of mechanical energy. It is a height of capital H from the ground. An object is dropped from H height. Let's say this is position 1. Now it moves and reaches to ground after some time. We have to prove that the total mechanical energy at any point of its journey is constant. That is, total mechanical energy is equals to constant. Here the system is mechanically isolated, that means no air friction is working. We will consider 3 points. This is point 1, this is some in between point 2, and just before touching the ground the point is 3. Let's say that this distance is h. Velocity at point 2 is v1 and velocity at point 3 is v. We have to prove that total mechanical energy at any point is constant. That means energy at one point is equals to energy at second point is equals to energy at third point. So let us begin. The energy at first point is equal to, at that point the object is dropped, so it is not having any kinetic energy, it just have the potential energy. The potential energy is at height of capital H is given by mgh, where m is the mass of object, and this will be the total energy. Now energy at E2. At the point of E2 or at the point of 2, the object is at certain height from the base and it is also having some velocity. So at point 2 it will be having both kinetic and potential energy. The potential energy will be the height from the ground will be capital H minus small h. So potential energy will be half m, it will be mg h minus h. Now we have to find this speed. It travels from rest and moves a distance of h. So displacement is h. We can use third equation of motion, v1 square is equals to initial velocity 0 as it is dropped plus the distance traveled is h. Put this value in this equation. E2 will be half m v1 square. v1 square is 2gh plus mg capital H minus mg small h. This 2 and 2 will get cancelled out. This will be plus mg small h and this is minus mg small h. So this 2 will get cancelled out and E2 will be equal to mg capital H. Now the energy at point 3. As at point 3 the object is just about to touch the ground, the potential energy at point 3 will be 0. So it will be having only kinetic energy. So at E3 only kinetic energy, and that is equals to half mv square. Again we will use Newton's third equation. V square is equals to u square, that is 0, plus mg, the total height travel is h. This is 2gh. So put the value in this equation. E3 will be half m into 2gh. This 2 will get cancelled out. So E3 will be equal to mg capital H. The total mechanical energy at all 3 points is same, that is equals to mg capital H. So the mechanical energy is conserved. Now let us see some examples based on conservation of mechanical energy. A block of mass 8 kg is released from the top of an inclined smooth surface as shown in figure. If spring constant of the spring is 200 Newton per meter and blocks comes to rest after compressing the spring by 1 meter, then find the distance travelled by block before it comes to rest. This is a block of 8 kg. It slides down the smooth inclined surface, that is, it is frictionless. After compressing the spring by 1 meter, the block comes to rest. We want to find the distance traveled by block before it comes to rest. Let's say it comes to rest at this point, and the distance traveled by it up to this point is d. If this distance is d, this angle is 30 degree, so we can find this height h using trigonometry. Sine 30 degree is equals to h upon d. So h will be equal to d sine 30 degree. Now when the block starts sliding, it will gain some kinetic energy and lose some potential energy. So the loss in potential energy is converted into kinetic energy at a certain point. At this point, the object will start compressing the spring and will come to rest after traveling a distance of 1 meter. So whatever the energy this block has gained by losing this much of potential energy, it is completely being transferred to the spring. So we can write the energy lost, the potential energy lost by block is equals to energy gained by spring. So mg, h is d sine 30 degree, is equals to half k x square. Now we want to find the value of d. Mass is 8, g is 10, into d. Sine 30 will be 1 by 2, that is equals to half, into k is given 200, and spring is compressed by 1 meter, so 1 square. This 2 will get cancelled out, this 10 will get cancelled out, so d will be equal to 20 by 8, that is equal to 10 by 4, that is 2.5 meters. So the object will travel a distance of 2.5 meters along the plane. In this example, a simple pendulum of mass m and length L is held in position at an angle theta with vertical. It is released from this position. We want to find the speed with which it will pass the lowest position. This is a bob mass system. This is bob of mass m. The length of the string is L. It is displaced by an angle of theta from its equilibrium position to point A. Now from this point it is being released. We want to find with what speed it will cross the bottommost point, that is point B. Here for the reference we will take this bottommost point to have zero potential energy, or take this point as a reference point. So at this point the potential energy is 0. So at point B the object or bob will have only kinetic energy. When it is released from A, so at this position the velocity will be 0. That means kinetic energy will be 0. So at point A, it will be having only potential energy due to this height difference. So at point A, it is having only potential energy, and at point B, it is having only kinetic energy. If we find the height we can use the energy conservation, that is potential energy is equals to gain in kinetic energy. So first let us find this height. If this angle is theta, this is L, so the line SC is equal to L cos theta. So BC will be equal to, this is total length of this string, that is L, so L minus this much height is L cos theta. So BC will be equal to L into 1 minus cos theta. So the loss in potential energy will become the gain in kinetic energy. So loss in potential energy at A is equals to gain in kinetic energy at B. The loss in potential energy will be equal to mg into L 1 minus cos theta, and gain in kinetic energy will be, let's say, half mv square. We want to find the speed with which it will cross the point B, so this m will get cancelled out and v square will be 2gl into 1 minus cos theta. Taking square root on both the side, we'll get v is equals to under root 2gl into 1 minus cos theta. So this will be our answer. In this example, a stick of mass m and length L is pivoted at one end and it is displaced through an angle of theta. We want to find the increase in potential energy. Here, if we see the rod, the change in height for the different lengths is different. In that case, we have to consider the center of mass. Let's say center of mass is located at this point in vertical position, and after the theta angular displacement, it is situated at this point. So we will just find the change in height of center of mass. We can treat this whole stick as a single point mass concentrated at these 2 points. So the center of mass will be the geometric center as it is uniformly distributed. So this length is L by 2. We want to find this height difference. This length will also be L by 2. So change in potential energy of center of mass will be equal to, for reference we are taking this line as this point as a reference point, that means potential energy at this point is 0. So the potential energy at this point, or the change in potential energy, will be the total mass m into g into this height. Let's say this height is x. So x. Now we have to find this height. This length is L by 2. This length is also L by 2 and this angle is theta. We want to find this height x. So from this we can write this much height is L by 2 minus L by 2 cos theta, that is equal to x. The total height is L by 2 and this much height will be L by 2 cos theta. So put this value in this equation. So potential energy will be equal to mg, take this L by 2 common, into 1 minus cos theta. So this will be our final answer. In this example, the block is released from a smooth inclined plane. This block of mass m is released from smooth inclined plane of angle of inclination theta, and it comes to rest after traveling a distance d on a rough surface. So this surface is rough and this inclined plane is smooth. The object must have gained some kinetic energy at this point. Let's say speed is u. After traveling a distance of d on a rough surface having coefficient of friction, let's say mu, it comes to rest. We want to find this value of mu. Now we can use the conservation of energy here. The energy at this point is completely purely potential energy. While it moves along the inclined plane, while reaching at the bottom, the completely potential energy is lost and kinetic energy is gained. Whatever kinetic energy it has at this point, it has been used in overcoming the frictional force on the distance d. We want to find the coefficient of friction. So first of all, let us find what is the velocity of the block at this point. For that, we will use conservation of energy, that is loss in potential energy is equals to gain in kinetic energy. Here, the loss in potential energy can be written as, let's say this is height h. So sin theta will be equal to h by x. So h will be equal to x sin theta. So loss in potential energy will be equal to mgh, that is equals to mgx sin theta, and that is equal to gain in kinetic energy, so half m u square. This m will get cancelled out, so we can write u square is equals to 2gx sin theta. Now this is the velocity of the object before starting on motion on the rough surface. After traveling distance of d, it comes to rest. We can use Newton's third equation, that is v square is equals to u square plus 2as. So final velocity is 0. Initial velocity is 2gx sin theta plus 2a and distance is d. So the acceleration 2ad is minus 2gx sin theta. So the acceleration will be, this 2 will get cancelled out, minus gx by d into sin theta. This negative sign shows that the acceleration is in the opposite direction of motion. Now this acceleration or this retardation is due to friction. The friction force is given by mu n, and the acceleration is frictional force upon mass. So mu n upon m is equals to, we are just considering the magnitude, so is equals to gx by d sin theta. The normal reaction is mg, so m will get cancelled out and g will also get cancelled out. We can find mu is equals to x by d sin theta. So this is our final answer.